I'm here to talk to you a little bit about some research that my advisor, Noah Snyder, and I have been doing concerning measuring river geomorphic change using a small unmanned aircraft system, or SUAS. So another name for SUAS is drone. It's a certain type of drone, and the one that we're using in our study is pictured here. This is a remote control helicopter mounted with a camera capable of taking aerial photographs and video. So drones have been in the news quite a bit lately, doing all sorts of questionable things. I'd like to say that ours is a friendly drone. This is a little mascot that'll be appearing throughout this presentation to kind of cue you in on the activities of what I've been doing there. Okay, so why do we care about drones and measuring river geomorphic change? So this is, we've had research suggest that there's been an increase in high magnitude flooding events, such as Hurricane Irene, shown here in a NASA image, making landfall in New York City in late August. The frozen north of New Hampshire at Bretton Woods. We've got a study site on the White River, central Vermont, site on the Sauhegan River in southern New Hampshire, and then several sites in the Upper Saco River watershed, which is about an hour's drive east of here. A site on the Wildcat River in Jackson, New Hampshire, a site on the Rocky Branch in Bartlett, New Hampshire, and a site on the main stem Saco in North Conway, New Hampshire. So I'm going to focus in this presentation on the site on the Wildcat River, just to give you an idea of how the workflow works for measuring topographic change here. So this is a picture of the site in Jackson. That's me on the bank on the upper left, and flow is coming towards you guys, so downslope is this way. We've got a pretty, you can see erosion on the cut bank in this image, and there's reason to believe that we would be able to take repeat topographic surveys of this site and sense change there. So it's a good place to test out our method. So this is the technique that we're using in order to create digital elevation models of the study sites. It's called structure from motion. And with the drone, we take multiple overlapping aerial photographs, and there's parallax that you get from these changes in perspective. You can input these images into a computer program written by some Russian coders that uses pixel matching algorithms to reconstruct a self-referential three-dimensional model of a scene. So it sounds like a lot. I can answer questions again. But it's basically you've got a drone moving through the river channel scene like this. So this is the motion within the scene. And then you get structure, three-dimensional point cloud of the feature object from the change in perspective. So this is what a drone survey looks like. It's pretty quick and easy. That's the quadcopter there. I'm off to the right. It's maybe a 10-minute setup. You fly the drone at an elevation of approximately 50 meters, taking photographs normal to the river surface. And then you put those images into a computer program called Agisoft, and you get a three-dimensional model of the scene. So this is just kind of showing you the power of these small unmanned aircraft systems. This is a flyover of a site on the Sauhegan River in southern New Hampshire. Just to give you an idea of, this is fairly easy to do, and we're getting all sorts of information about the study area that we really, there's no other way to get this type of imagery other than flying a helicopter. And even then, you might not be able to maneuver it this well within the study area. So, yeah, you can just let this play out a little bit. You can kind of get a sense of all the stuff that's going on in the channel here. You've got a floodplain forming by the water over here. I don't know, there's go into more of that. But anyway, before we did the survey, we kind of wanted to get an idea of how accurate the total station was, measuring the same points at different time and space. So we know that if you measure a point with the total station, it's got sub-millimeter, or accuracy on the order of 1 to 2 millimeters. But if you measure the same point from different positions and different times, what's the accuracy introduced to that point from the GPS that's attached to the total station? So we found that that had a root mean squared error in all dimensions of around 3 to 5 centimeters. So that's kind of our baseline error. This is the sensitivity of the method that we know of. So I'll take you through some workflows about how we use this method. So we've got a channel cross-section. The dashed line is the water surface. Measure that cross-section with a total station and an SUAS. We also use points from this measurement to georeference the three-dimensional model created from the drone. We put these aerial photographs into PhotoScan and pick out ground control points within the image so that we can later go back and assign them values that we've measured with the TPS. So these just are some example photos from the Wildcat site. You can kind of get a sense of how you're able to see some topographic relief from the changes in perspectives in these series. So there's the cross-section. Then we import these, align these photos in PhotoScan to create a point cloud. This is what a point cloud looks like within the computer program. The blue rectangles are the aligned photographs that the program automatically places within the scene based on the overlapping pixels. And then the cross-section also appears in this scene, but it's not that distinct. So this is, we have a couple of methods of how to process this point cloud. The first method I'm going to talk about is this one where we take the point cloud within PhotoScan and build a mesh from that, which is basically an interpolated surface of the river channel. Then that's what the mesh looks like. That cross-section appears there. And we create a digital elevation model from that mesh, export it. This is what the an example digital elevation model looks like from the Wildcat site. This is about an 8 centimeter pixel resolution DEM. You can see that it resolves individual class pretty well within the scene. It's a pretty high resolution image. I mean, George was talking about LiDAR, which is meter scale resolution. This is centimeter scale resolution. So it's pretty cool. So you import these DEMs into ArcGIS, and then you can take DEMs from other surveys and do a difference on them and get an idea of quantified where erosion and deposition have been taking place within the scene. So another method that we can do is we can, PhotoScan is a bit of a black box in terms of georeferencing. You're not really, we wanted to test the confidence of how well it's georeferencing the image. So there's a point cloud, a raw point cloud processing program called Cloud Compare where you can match up the actual point-to-point georeferencing, and then you can create a DEM from an interpolation of that point cloud and import that into ArcGIS and do serial DEM comparison, much in the same way as the method 1 to quantify the geometry change. And the third method is to not even bother with reconstructing a DEM and do point cloud to point cloud comparisons. So I haven't done this yet, but this is where the research is going to see, compare which method is going to give you the best sense of change. So these are this is an example cross-section from the Wildcat River site, the upstream cross-section. The blue line is the measured cross-section we did with the total station survey. The white dotted line is the water surface that we measured at the site. So here I'm going to import this is our SUAS, or drone survey elevation data. So we see a systematic offset on about 10 centimeters across the whole section, where the drone is measuring points 10 centimeters higher than we are with the total station, despite the georeferencing. So that's a little bit somewhat problematic. But if we parse it out a little bit and say, okay, the drone survey is probably not going to be able to reconstruct the topography of certain surfaces, certain surface characteristics, as opposed to other surface characteristics. So namely, subaerially exposed places versus subaqueous exposed in the channel underwater surfaces. So we find that the subaerial exposure using method 1 is about 8 centimeters higher, whereas the subaqueous is measuring 13 centimeters higher than the drone survey, which isn't, it's hard to measure subsurface topography because there's water current, which is distorting the light. So method 2, we find that there's an offset of about 11 centimeters, so they're pretty comparable techniques. But interestingly, in this, the subaerial is better resolved with method 2 versus the subaqueous. So if we take all the points that we measured with the total station and the drone within this survey, which is 190, we we find that method 1 has a 9.8 centimeter offset higher than the total station survey results. And then method 2 is measuring elevations about 8.7 centimeters higher than the total station. So what I did is I measured this site in June 25th, 2014, and then again on July 14th, 2014, I did 2 georeference DEMs. And then I did a serial DEM comparison using method 1 of these 2 DEMs to get a sense of what's the elevation change within the image. So this is the result of that geomorphic change. We've got areas in blue on this map, mostly over to the your right, show deposition, and then the area, the channel, the cut bank that I was showing you earlier in the presentation that looks to be eroding does show erosion on the order of less than 20 centimeters. So this is a preliminary result that we've achieved here, but it is tempting to kind of say, you know, this looks kind of believable, and I don't know. I'm going to work on trying to evaluate how believable this is, but it is, it is encouraging. So another kind of interesting thing is you can, because the aerial photographs that we're also reconstructing using these images are such high resolution, you can track individual class transport within the images. So it's kind of a double check in a sense. Do we believe that there is erosion happening in this image? So I'll draw, even though you could kind of do a scavenger hunt throughout the whole scene and in this image to see what are the changes that are going on, I'll just highlight this class in the magenta circle. This is its position on June 25th, so this is about like maybe a 10 centimeter grain size segment. And then it's there in June, and then goes down there in July. I mean, this is, I can't say definitively that that's the same, cobble, but I don't know. You can see that there, if we kind of scan back and forth, you can see some differences. The water level is a little bit higher in the July image, but so that kind of monkeys it. But you can definitely see there's stuff moving around. So it's not unreasonable that we could have elevation differences in the channel. So if we look at the stream gauging data from the Saco River gauging station in Conway, New Hampshire, we find that the blue line is discharge over time. So this star represents the flow at the June 25th survey, and then lo and behold, a day after we did the survey, there was a 2-year flood event. So in terms of geomorphology, this is close to a channel-defined event where you'd expect geomorphic change to happen. So that was kind of lucky that we got that event. I like to think it's geologic intuition, but mostly fortune. And then that's where we measured it in mid-July. So we expect, as I mentioned in the earlier Hurricane Irene slide, the research suggests that these high magnitude flood events are occurring more frequently, as with potentially changing climate. And this is just a flood frequency analysis done at that Saco River gauging station in Conway, and we find that 2 of the top 10 highest magnitude flood events have occurred from the last 5 years. So up at the top is Hurricane Irene, all the way to the right, and then, this is kind of a surprise or an interesting finding, is actually the 10th biggest event occurred last spring during the ice out event, which is interesting. And seeing as how we've had, at least in Boston, a lot of snow this winter, I can assure you, the spring and throughout the Northeast, I think the spring, this is a picture of the site 2 days ago now, and I think it's safe to say that we can expect some geomorphic change to happen during the spring 2015. So future work, like I said, kind of evaluating how real is this change that we're seeing from the serial DEM comparison. We're going to resurvey these sites once the ice and snow have gone, we can get better images of the channels. Explore point cloud differencing to see how that compares as an analysis technique. And then also I've been talking to some other people that are working with structure from motion, and the reason, so we've been taking aerial photographs that are normal to the land surface just because that's how photogrammetry has worked since the first images, the first aerial photographs were taken in the US, and we got topographic maps from them. But because the drone is so maneuverable within the scene, we can actually take photographs from different perspectives, and that potentially could give us better, it's called convergent geometry, and that could potentially give us better resolution on those images. So I'd like to thank Boston College for funding this research, also Seth Kruckenberg, Gabrielle David, Oluwaseun, and Grace Stroke. So I've got some time